and let's enjoy the following 2 hours together. Now, the point where we stopped last week was just at the beginning of daemon processes. We were talking about how their name starts with a D and how they are long-lived and so on. But there is an issue about the way in which we start daemon processes. And usually students get a bit confused about why we are doing 2 calls to fork. What is this issue with the controlling terminal and so on? That is why I have added an extra slide in order to fill up those that void, basically. So we will be talking in the upcoming slides about sessions and process groups and controlling terminals. So just a short slide in order to give you some information about what is going on. I mean, why do we talk about sessions? What's the idea of a process group? I mean, why do we have to group even processes? What's the motivation behind it? Well, first of all, why a session? What is a session? A session basically is a large collection of processes. A session, oturum, is a collection of processes. Why does the kernel need to group processes? Reason number 1, because when a user logs out of the system, the kernel needs to terminate all the processes that this user had running. So the kernel, who is scheduling hundreds, thousands of processes, needs to determine which processes belong to this user. So it needs to be very fast in that. And so it needs some kind of an identifier in order to determine this. Now, you can have, of course, multiple sessions belonging to the same user also. Now, originally, when the user logs in, the user starts with a single session, and that session basically represents the process that represents the shell of that user as the user logs in to the system. Now, whatever descendants, children processes are created from that original process, they are considered in the same session. Of course, other processes can also create their own session as well. They can get out of that session and become session leaders for a new session as well. Long story short, a session is a collection of processes that exists only for logistic purposes, organizational purposes, so that the kernel can easily determine which group of processes move together and so on. Now, every session, you can have multiple of them. So every session contains multiple processes. So every session is tied to a single terminal. Now, what is a terminal in this case? The terminal can be the command prompt where you enter your commands. It can be a distant terminal that you have opened up through a secure shell to a remote computer. It can be it can be anything basically that can accept those commands, that can accept that input. But a session can have only one of them. A session can have only one controlling terminal, and it is to that terminal that the processes send their output and receive their input from. Yes, of course, we know that the standard input represents usually, very usually, the keyboard. But whenever you type something in the keyboard, if you have multiple open terminals, to which exactly is it going to go? So you need to also tie devices to terminals or controlling terminals. And you also need to associate those terminals with certain groups of processes, or in other words, sessions. Now, below these sessions, there is a second even organizational entity. So the large one is the session associated with one terminal where it receives its input from and sends its output to. But below the session, there is a second organizational entity that is also a group. Now, a group is just a collection, a small collection of processes. For instance, if you have, for instance, a compound, bileşik, a compound collection of commands, and it exists in order to enable us to perform job control. So in order to cancel, for instance, with Control Z, Control C, in order to suspend or cancel more than one processes. So if, for instance, I enter this command that you see on this slide, and if I try to cancel it, or if I try to suspend it, or continue it after having suspended it, I need to be able to target them with a signal, all of them. all of the commands in this compound command. And that is why we have process groups. So you need to also have some kind of an identifier to determine which processes go together. So if they receive a signal, they will receive it, all of them together. Long story short, sessions and groups are just means, araçlar. They are just means that enable the kernel to perform a finer level of control over process organization, process management, how to cancel them collectively, and so on. Most of the time for canceling them collectively for practical purposes. But be careful for the controlling terminal. Only one is associated with a session of processes. So you can have, for instance, a command prompt where you have multiple tabs, for instance, birden fazla sekmesi olan bir komut satırı. And all of those processes, all of those shells basically, they are under the same session. And you can have multiple such sessions. You can have multiple such controlling terminals. Now, that being said, now let's look at daemons. Now, daemons are no different than ordinary processes. A daemon is just a process. It doesn't have a different organization or different structure. It doesn't have different system calls. A daemon is a process like any other. So you also started with fork. You can also start it with fork and exec. It uses the same techniques for file input output and so on and so on. Nothing different. Now, there are a few minor differences with daemons. Now, why? Why are there differences? The differences exist because daemons are expected to run from the beginning of the booting process. So from the moment that the system is booted up, usually until the system shuts down. So we are talking about a process that must be usually user independent. So even if users log in and log out, etc., that process in the background still continues to execute. So it needs to be very careful about memory management, and it must be protected against accidental terminations. It must be protected against accidentally being sent a control C, a control Z, a sig term, sig int, and so on signals. And that is why we take certain precautions when starting these daemons. And one more thing, usually these daemons, they exist as a single instance. Sadece bir taneleri çalışabiliyor belli bir programda. So you cannot have two processes of the same daemon program running at the same time. So, for instance, you can ask this yourself. How do you make sure that a program cannot be run a second time if it is already running? Zaten çalışmakta olan bir uygulamanın ikinciye çalışmasını nasıl engellersin? So daemons also need to address this. So in general, long story short, here we have a list of items that need to be carried out in order to start the daemon safely. Long story short, the things that need to be done is to become a daemon, one, you need to, of course, perform a fork. Naturally, all the processes need to be started after a fork. But after a fork, the parent usually exits. So whoever created the daemon, the parent, usually exits, and the child continues. So that means the shell will return to its prompt. Yani komut satırında tekrar şeye dönüyor. İmleçe geri dönüyor. Yeni bir komut bekler hale geliyor. Now at this point, there are some interesting things happening. The child calls a very special function called set session ID, set SID, in order to start a new session. So it tries to leave the session to which its parent belonged in order to start a new session, meaning that since there is one controlling terminal associated with every session, it also frees itself of any association with a controlling terminal. Why? Why does it try to cut off the connection between the terminal and the daemon process that we started, so that closing the terminal will not kill the daemon? So it is trying to protect itself from being accidentally closed in any way. Now, of course, there is also the danger that if the daemon later also opens a terminal device actively, well, in that case, there is also a rule in the Linux world that If you don't have a controlling terminal and you open a terminal, in that case, that becomes your controlling terminal. So in order to avoid that, it also takes some additional steps. We will look at that in the following slides. It clears the process UMask, so to ensure that when the daemon creates files and directories, they have requested permissions. So, okay, that should be expected. It changes the current working directory, typically to the root, so that it will be disassociated from any home folders or anything. It closes all the open file descriptors that are, of course, inherited from its parent process. And not only that, but after having closed the file descriptors 0, 1, and 2, even 0, 1, and 2, so input, output, and so on, the daemon will usually open the dev null device, to make sure that all of these descriptors refer to it. Now, what was the dev null device? I'm sure that you have encountered this in the past years. Do you remember the dev null device? Ne yapıyordu arkadaşlar bu araç, bu cihaz? Since it takes place in the dev directory, it means that it's a device, of course. And what the null device is, basically, it's a black hole, kara bir delik. Whatever you send to it, so let's say that you redirect your output to dev null, it disappears. If you try to read something from it, there is nothing to read. So basically, it is a black hole. It is basically arkadaşlar sifon gibi. You just use it in order to throw your garbage to it. So whatever you want to ignore, you just throw it there and it disappears forever. So the daemon redirects its 0, 1, and 2 to dev null so that whatever it prints, whatever it produces, it goes usually to dev null so that it will not need to be printed anywhere. So it completely disappears. It tries to remain behind the curtains as much as it can. Tamamıyla perdelerin arkasında kalmaya çalışıyor arkadaş. Ne girdisi, ne çıktısı, ne herhangi bir associated terminal, nothing. Tamamıyla gizlenmeye çalışıyor arka tarafta bu kerata. Now, if we look at the details, of course, this is a slide that we saw last time. It should have been here. If we look at the details now, how to prevent double inclusion, how to prevent double execution, rather. So how do you stop a daemon from being executed twice? Now, let's look at this. Here we have the header constants for a standard daemon initiation. So bitmask values for certain flags. So whether it should change the current directory or not, whether it should close the all the open files or not, whether it should reopen or not, standard input, output, and standard error, whether it should use the UMask or not, etc. So these are the available flags, just in order to control our behavior. And of course, we have the become daemon function that will convert this process into a daemon process. Now, just in order to remind the previous remark, stdin, standard out, and error are closed so that the daemon can detach successfully from the controlling terminal it was started from, and also so that the daemon won't write to the terminal when it is running, so that it will be as invisible as possible. Now, how does the process become a daemon? Now, it receives certain flags. Okay, now this is a custom function. This is not a function. This is not a system call. This is not a library function. This is a function that is written by every developer depending on their needs. And the idea is basically always the same. Make sure that there is no controlling terminal. Update the UMask, so the mask that is used for the permissions of files created by the daemon. Make sure that you change your current working directory if necessary, and so on and so on. Let's look at those steps. If we were actual professionals doing system programming, this is pretty much something like this that we would be using. So first, now there will be two forks. Now this is the first fork. Now first fork, in order to create the new process. So now we have a clone. If it returns -1, well, that means we have failed in fork, so immediately we return, there is nothing to do. If it is 0, well, that means we are in the child now. Now, the child immediately gets out of the switch, whereas the parent, in default, it exits. So the parent terminates, and from whatever shell we executed this command, this process, the shell now returns to its prompt. Now, the child, what does the child do? Now, the child detaches itself from the session of its parent, and of course also from the controlling terminal of that session, and becomes the leader of a new session. And in this new session, there is only this new process, nothing else, and no controlling terminal. But this still means that it can still acquire a controlling terminal if by any chance it opens a terminal device. Now we also need to eliminate that possibility. So in order to eliminate that possibility, we call fork again, second time, and we ensure that this time we will not be the session leader. So, and thanks to the second fork, at this point, now there is no way that this process can acquire one more terminal, one more controlling terminal, even by accident. It cannot happen. And of course, the parent, the one that we had just cloned previously, it also exits. Why do we have two forks? In order to eliminate the possibility of acquiring a controlling terminal. Why do we want to eliminate that possibility? Because if by any chance we have a controlling terminal, well, in that case, we can accidentally receive signals, we can accidentally produce an input, output, or whatever. We need to detach ourselves as much as possible. Then, very easily, we just have some controls, whether we want to call UMask, whether we want to change the current working directory, close the open files, all of them, whatever is available, whatever is open, and so on. Of course, at this point, we also redirect all of the input, output, and error to the dev null device to make sure that whatever we produce as output also disappears forever. So this is a pretty much standard way of demonizing, converting to a daemon, a standard process. Nothing fancy about it. It's not a system call. It's not a library function. It's just a standard function in order to take the necessary steps. Of course, at this point, you might wonder, why is there all this anxiety or preoccupation about disassociating from a controlling terminal? I mean, is it that much of a big deal, really? Well, apparently it is. Apparently it is. So the POSIX world is doing whatever it can in order to produce robust programs. Even if there is a small chance of something going wrong, it is doing the best that it can in order to eliminate that possibility. And that is why nowadays, even in 2021, the longest running systems, hani kapatılıp açılmadan, reset atılmadan en uzun süre çalışan sistemler hala POSIX sistemleri. Windows'lar değil. And I think the record is, what was it? Kaç yıldı ya? What was it? 20 years, 30 years? I don't know. There is such a system which holds the record that hasn't been reset in I don't know how many years. There is a record on that, and it's a Unix or Linux system. Anyway, now daemons of course perform some specific tasks, such as providing a network login facility, serving web pages, and so on and so on. Here we have a summary of the previous example. So it performs a standard sequence of steps. It is the same for all the daemons, including multiple calls to fork, 2 calls. And of course, setting the session ID. Now, of course, this still means that daemons can receive signals. I mean, somebody can execute the command kill, give the name of the signal, and give the process ID of the daemon. They can still receive signals, and of course, they need to be able to handle those signals. And they should definitely handle signals that suspend them and restart them, because those services sometimes they can block or anything, and you need to be able to reset and restart them. But just the services, not the entire system. So they usually handle those signals. Now, I will not be asking you to implement any daemons, so don't worry about it. But know that these daemons exist. They are running even as of now in the systems that you are using. And the only difference between them and the other processes on your system is that they have just taken these additional steps that I have mentioned before in order to make sure that they are not accidentally closed, in order to make sure that they have no associated terminal, no input or output, and so on. So they just wait for somebody to ask them something through a socket, through a file or whatever, in order to respond to those requests. Yani arka tarafta şöyle yardımcı olarak bulunan minik süreçler arkadaşlar. Bayağı bir uzun soluklu ama oradalar kendileri. Evet. And that is the end of week 5, which means now we can start with the contents of week 6. So we save that. Now week 6 is, the slides are available on Moodle, so you can download them. Okay. IPC. Now let's forget daemons, because we have something more important to talk about. Inter-process communication. These 3 letters, what do they mean? Now the kernel has went to a great length in order to make sure that processes have really distinct memory spaces. It has gone to a great length, çok uğraştı, it has gone to a great length to make sure that processes cannot disturb each other. And if by any chance a process attempts to read or write a memory address that doesn't belong to it, of course it will receive the well-known segmentation fault or Sigge-Segge signal and terminate immediately. So that is very strictly forbidden, prohibited in the world of the kernel. But that also means that it also becomes difficult for processes to communicate. So what happens when I have multiple processes, 2, 3, 4, 10, that want to exchange data? Maybe unidirectionally, tek yönde, or bidirectionally, from process A to B, from B to A. How do you transfer data? How do you communicate between processes? That's what IPC is. Süreçler arası iletişim. And that will be the topic of this lecture. Now, IPC refers to the mechanisms an operating system provides to allow processes to manage shared data. 3 broad categories. It involves 3 broad categories. Now, we have already talked about signals. And don't worry, we are done with signals. We will not be talking about signals in detail again, but just know that, or as you already know, signals can be used for communication between processes. And even for synchronization, as is the topic of your current number 2 homework. Now, there are 2 main things, 2 main concepts under the IPC roof. The first one is, of course, communication, how to exchange data between processes. How do I send data from process A to process B? And 2, synchronizing. Hocam ne alakası var? Niye synchronization söz ediyoruz şimdi? Ne güzel iletişimden söz ediyorduk. Good question. Kendi kendime soruyorum, kendi kendime yanıtlıyorum. Bu da ayrı bir eğlence. Synchronization, eş zamanlama. Eş zamanlama. Why do we mention synchronization? We are mentioning it because you cannot have robust communication, you cannot have effective communication without some even rudimentary, even basic form of synchronization. Just imagine a very simple scenario. Process A is sending data to process B. Now, process A is sending the data, but is process B ready to read the data? They need to synchronize. Or process B is expecting data, but how does it know that process A is ready to send the data, or whether it has sent the data or not sent the data, or whether it is available to send the data? They need to synchronize, even for a very simple task of sending data from A to B. This one needs to be ready to send, and this one needs to be ready to read, to receive. Even in that very simple scenario, they need to synchronize. Synchronization is a big issue. It is a very important issue. And it is usually the reason why many programs fail. Because it is not that easy to solve. Especially the more intricate the communication is, the more complex the communication is, not just from A to B, but maybe from A to B, from B to C, from C to A, etc., just like the stuff that is going on in your homework. Well, in that case, synchronization is not easy. So you need to pay attention, because even if you leave just one possible scenario unhandled, aklına gelmemiş, düşünmediğin bir problem dahi kalsa, it is enough to freeze, to block, to crash the entire group of processes. And that is why there are a lot of techniques for synchronization. We will take a look at them. Some of them are very powerful. Some of them are very specific to certain cases. But that is one of the main issues that will be encountered. I mean, this is why I also told you about this during our first week. I told you that the two main things that we will be talking about in this course will be communication and synchronization. Those are the two main things. And we have finally reached in week 6 to the first case. Why first case? Why? Is there a second? Yes. This is the case of inter-process communication. So how to communicate and synchronize between processes. And we will dedicate a few weeks to this. And then we will do the same thing, but with threads. How to communicate and synchronize between threads. Birisinin mikrofonu açık. Soru mu var? Mikrofonumu unuttu. Herhalde mikrofonunu unuttu. Peki. Okay. Now this is a nice graphic of all the methods that are available for in the category of IPC. So whenever we talk about communication and synchronization between processes, these are our options. The traditional options that exist in every POSIX compatible system. So for communication, we have shared memory systems, anonymous mapping, filed mapping, memory mapping, shared memory, System 5 shared memory, POSIX shared memory. We also, for data transfer, we have message systems, byte streams, pipes, FIFOs, sockets, pseudo terminals. We of course have the signals for synchronization, standard signals, real-time signals. We didn't see that distinction. It's beyond the scope of this course. And of course, for synchronization, we have semaphores, which also are subdivided into System 5 semaphores, POSIX semaphores, named semaphores, unnamed semaphores. We have file logs, such as record logs, in order to log only a section of a file, or file logs in order to log the entire file. We have mutexes, we have condition variables, and so on and so on, which are only, these last two are only available in threads. So this is a general panorama, an overview of all the tools that are available. Now, in the context of this course, in this lecture, we will take a look at most of them, with the exception of messages. We will not look at message queues, and we will also not look at real-time signals. But all the rest, I think, also not pseudo terminals, but all the rest we should be taking a look at in the context of this course. So step by step, starting from today, we will study all of these synchronization and communication means that are available to us. Now, first, communication. Let's forget about synchronization for now, and let's talk about communication. We have 5 big categories. Remember, I'm not counting in messages. That is beyond the scope of this course for now. Now, number 1, shared memory. Shared memory is a concept, a tool that is available to us that permits processes to communicate by simply reading and writing to a shared memory page. Basically, the idea is very simple. You have 2 processes that want to communicate, and they both say to the kernel, look, kernel, we know that we are distinct processes. We know that you don't allow us to have a common memory space, a common address space, but we are actually requesting you to set aside a section in the memory, in kernel memory even, so in the, well, not kernel memory, in random access memory, a special section that will be accessible to both of us. Bellekte ikimizin de erişebileceği bize bir yer aç. That's the whole idea of shared memory. And once that is available, both processes can read and write to that common location. O ortak alana ikisi de yazıp çizebilir. Yazabilir, okuyabilir. Mapped memory, on the other hand, is similar to shared memory, but it is associated with a file in the file system. Just to give you the general idea, both processes, they select a certain file, they agree on that beforehand. We will talk about this in detail. This is just the introduction. Both of them agree that there will be a certain file in the file system, and both of them will be reading and writing there. But the difference with respect to just regularly selecting a file, the difference between a file and a mapped file is that the contents of that file are reflected onto memory, and whatever you read and write in those memory locations is immediately reflected also to the file. Yani bir belge düşün. Belgenin içeriği yansıtılmış belleğe ve oraya sen dokunduğun anda o bellekte bir şey yazıp çizdiğinde anında tekrar o dosyaya yansıtılıyor. Biraz bir özel bir durum. Hani işin içinde bir belge var. Shared memory'ye çok benziyor ama işin içinde ayrıyeten bir de dosya da var. We will get to that. Now, pipes and FIFOs. We will talk about pipes and FIFOs this week. Now, this is the simplest, one of the simplest ways of communication between processes. Very easy to implement. Now, pipes, they permit sequential communication. Sequential. Şimdi communication'da sequential communication'ın farkı ne? Now, sequential communications means that you transfer the bytes one by one after the other. Sırayla. Şöyle bir şey gibi, ırmak gibi, nehir gibi hayal edebilirsiniz. Bir stream. Akıyor şöyle byte'lar. Seri bir şekilde. From one process to a related process. Pipes can only be set up between processes that are related. Akraba olan, veli çocuk ilişkisi olan süreçler arasında sadece. FIFOs, on the other hand, they are very similar to pipes, except that even unrelated processes can communicate using them. So pipes and FIFOs very similar. The only difference, pipes can be set up between related processes, FIFOs, even between unrelated processes. And then we have sockets, which have a very important advantage with respect to all the other methods, and that is sockets are the only mechanism available for communicating between unrelated processes on different computers. Because all the other methods, they only allow communication between processes executed on the same computer. Eğer farklı bilgisayarlarda çalışan iki süreç arasında iletişim kurmak istiyorsan soketler dışında başka seçeneğin yok POSIX'te. Windows dünyasında FIFO'ları da kullanabiliyorsun. O ayrı konu. Oraya girmiyorum. Böyle. What are the criteria? How do we categorize communication mechanisms? What are the properties? Well, number one, does it allow communication between related processes or also between unrelated processes? Does it allow communication between processes on the same computer or also between processes on different computers? So this is a way that we can use in order to categorize them. Whether the communication is limited to only writing data or reading data. So is it bidirectional or unidirectional? How many processes are allowed to communicate? Does this mechanism allow n processes to communicate or just 2 or 3? And last, whether the communicating processes are synchronized or not. So does the mechanism that we use also come with integrated synchronization mechanisms? Hani eş zamanlama işini kendisi mi hallediyor bu mekanizma yoksa bizim mi bunu kurmamız lazım? These are the criteria that we use for categorizing communication mechanisms. Okay, now let's look at them. But before that, of course, a very short look to synchronization. We will not talk about synchronization today, but just a small introduction. Semaphores are the number one tool that we use for synchronizing processes. In order to access shared memory and so on, they are very, very useful. They are very old, from the 1960s. They are due to Edgar Dijkstra'nın icadı. They are very, very effective. File logs. Now, this is only a modest Yani mütevazi bir eş zamanlama mekanizması, a modest mechanism for synchronization that can be used in order to coordinate the actions of processes that operate on the same file. And that's all. That's all. Mutexes and condition variables, which collectively are known as monitors, they are used only between threads, not processes, not between processes, only between threads. We will talk about threads when the time comes. Don't worry about it. And what is important about mutexes and condition variables is that theoretically, they can solve any synchronization problem. Of course, at this point, you might ask, hocam, semaphores, can't they solve any synchronization problem? No. No. There are synchronization problems that you cannot solve with semaphores. But with mutexes and condition variables, you can solve anything. Theoretically, there isn't anything that is unsolvable with mutexes and condition variables. Any synchronization problems. Yoksa hayatın anlamını çözmeye kalkmayın onlarla. Now, of course, IPC has continued to grow. It has grown beyond POSIX and Unix at the time, beyond just simple communication between process A and process B. And nowadays, there are very advanced technologies like remote procedure calls, remote method invocations. I mean, nowadays, you can even execute a method of an object running in a process at a distant machine from here and collect the output of that method from here. Now, all of this behind the scenes, behind the curtains, underneath it is still using these fundamental mechanisms. So sockets and pipes and FIFOs, they are still there. But nowadays, we are using mechanisms that are layered on top of them, on top of them, and on top of them. So we have very advanced mechanisms like .NET Remote and SOAP and so on, the Spring, etc. Frameworks, Hibernates, and so on and so on. But underneath them all, we still have the good old sockets and pipes and FIFOs and shared memories that are being implemented. So this is the basis of it. This is the base of it. And even if in 10 years there will be completely different technologies, so not to Spring or Hibernate on RMI or RPC or whatever, these things will still be there. The sockets will still be there in 10 years. Those things, they have been here for the last 80 years and they do not intend to go anywhere. Sorry, for the last 60 years. Okay, any questions? Okay, no questions then. So let's talk about pipes. Now, this is the oldest and simplest method of communication between two processes. One pipe allows communication between two processes. Two pipes allow communication between four processes, if we want to. Now, a pipe is a communication device that permits unidirectional communication. Tek yönlü iletişim. One side will write the data, the other side will read the data. Borudan içeri giriyor. Pipe boru demek zaten. The data enters a pipe from one end and exits from the other end. That's it. Pipes are serial devices. It means that the data is always read from the pipe in the same order that it was written. So if you send first byte X and then byte Y, well, that means byte X will arrive before byte Y. Serial device. Hangi yönde giriyor, o yönde çıkıyor. First in, first out. Typically, a pipe is used to communicate between two threads in a single process or between a parent and a child process. Typically. Now, pipes are used also, of course, in the shell. So whenever you use the pipe symbol, such as in this case, what does this command do? Can anyone tell me? Bu komut ne yapıyor arkadaşlar? Biri söyleyebilir mi bana?
I think it's word count.
Yes.
So it counts the words.
But there is also a L there.
I'm not sure about that.
So if you use L, in this case, it should be counting the lines. So ls will give you the current directory listing, and the word count command will count the number of lines there. So it will give you the number of lines. So for instance, if I take this, so it tells me that there are 15 lines of output. So what it did was it executed ls, it took the output of ls, and it gave it as input to the word count command. So basically we created a pipe, just like you see it at the bottom of the slide. The output of ls became the input of word count. So basically we have a pipe there. So it is no coincidence that this symbol is called a pipe, because it is using behind the scenes a pipe, the pipe IPC mechanism, in order to set up a communication between these two independent processes. We have one process for ls, one process for word count, and we have a pipe connecting the output of the first to the input of the second. So this is another way of looking at the same thing. I mean, even if you didn't have a pipe and you use two commands like this, so ls, l, so line by line output, in this case, that is output to my.file. So we are printing the current directory listing and outputting it into a file. And then we are, for instance, giving that the file as an input to sort, in order to sort those lines and output it on the screen. Now the output of, it's not ln. This should be ls, not ln. Niye değiştirmiyorum bunu ya? Allah Allah. Anyway, so you can of course write the same thing by using a pipe and thus eliminating the need for a file. So the output of ls becomes the input of sort in this case. Okay, let's look at the details a bit. So how do you set this up? Through system calls. Now, first of all, the pipe is a buffer. Is a buffer that is maintained in kernel memory, not in process memory. It is kept in kernel memory, and it usually has a very limited capacity, often 64 kilobytes. So it is quite small. The size is not fixed. It depends on the system where you're executing it. In some systems, it might be 128 kilobytes. In other systems, it might be 32. So do not always assume that it is 64. Now, what is nice about the pipe? I mean, bundan hoşlanmamızın sebeplerinden bir tanesi is that it also provides us with a basic synchronization mechanism so that we don't have to worry about synchronizing the reader and the writer. What kind of a synchronization? If the writer process, yazan süreç, writes faster than the reader process consumes the data, and if the pipe is full and cannot store more data, then the writer process blocks until more capacity becomes available. So you have two processes. One of them is writing data, producing data, sending it to the pipe. And there is another process that is reading data, so it is consuming the contents of the pipe. Now, if now the writer writes faster than the reader, in that case the pipe will start to fill up. Boru başlayacak dolmaya, çünkü diğer taraftan yeterince hızlı çıkamıyor. Well, in that case, when the pipe becomes full, the writer process will be blocked. By whom? By the kernel. The kernel will tell the writer, stop now, the pipe is full, wait until there is some more room. So it will be taken away from the queue of ready processes and put to the queue of blocked processes. Who does that? The kernel, automatically. So you don't have to worry about it. Similarly, if the reader reads faster than the writer and there is nothing to read, what happens then? Does it fail? No. The kernel tells the reader to block until data is available. So the kernel takes the reading process from the queue of ready processes and puts it to the queue of blocked processes. Until when? Until there is some data to read. It's done automatically, so you do not have to worry about it. So as soon as you set up a pipe between two processes, you're ready to use it. No worries about synchronization or anything. Now, this is good. This is quite simple and effective and practical. But of course, there are disadvantages. The disadvantage is that you can use the pipe only between related processes. Related. Yani one of them will be the parent, the other one will be the child. They have to be related to be able to use the pipe. Let's look at the details. How do you set up a pipe? Well, very originally, you use the system call pipe. Now, the pipe system call, available in the Unix standard header file, receives as argument an array of length 2, an integer array of length 2. Okay, and what happens? Well, basically, it returns 0 on success and -1 on error, and of course it sets the error global variable. Now, you supply it an integer array of size 2. Then you call pipe, and what pipe will do is, it will store the reading file descriptor in array position 0 and the writing file descriptor in position 1. So basically creates a pipe, and it tells you position 0 of this array is the file descriptor that you can use in order to read, and the writing position, the writing file descriptor is in position 1. Sıfırdakiyle okuyabilirsin, birdekiyle yazabilirsin. Al sana boru. That's what it does. Any questions? Example? So here we have the integer array of size 2. We have two file descriptors. We have two integer variables. We call pipe. Of course, we should be controlling for whether it returned an error or not. And then we set 0 to the read file descriptor and 1 to the write file descriptor, and we are ready to use them. They are already open and ready to use. So whatever we write to this file descriptor, we will be able to read it from this file descriptor. But for now, we only have one process. So it doesn't really make a lot of sense to be using reading and writing in the same process. It would be very useful if we had two processes. Well, that's why we have fork. Now, a process's file descriptors, of course, cannot be passed to unrelated processes. So you cannot have a file descriptor open in one process and give it to some other process. It doesn't work that way. File descriptors can only pass from parent to child. That's the only way to give a file descriptor from one process to another. So when a process calls fork, the file descriptors that are open in the parent are, of course, copied to the new child process. And that is why pipes can only connect related processes. So the parent process calls pipe, it creates a pipe, and it has access to the writing and reading end. Then it calls fork, so that means the child process also has access to the writing and reading end. Now, after fork, the parent closes, for example, the reading end, so this is gone, and the child closes the writing end. Well, in that case, whatever the parent writes to the pipe, the child process will be able to read it. So two stages: one, create the pipe; two, close the unnecessary file descriptors. Sorry, call pipe, call fork, and then close the unnecessary file descriptors. And there you have a pipe set up to use between a parent and a child. Of course, at this point you might ask, hocam bunu ödevde kullanabilir miyiz? Hayır. Ödev, o yüzden yazdım ödevde. Sinyaller dışında hiçbir şey kullanmayın. Eş zamanlama için ve iletişim için. Bunlar ayrı. Bunlar bir sonraki ödevlerin konusu. Any questions so far? Okay, here we have now an example. Now, before we proceed to the example, we will take a break for 5 minutes because it is a bit of a long example. It will take 10 minutes to process it. So we are stopping for 5 minutes and we will continue at 9:28. 9:28'de görüşmek üzere arkadaşlar.